switch over. Power on. Okay. Computer set, document camera set to PC2. I have to switch it at a different spot. Haha. This is not my normal room, as you guys are aware. Okay. So. I'll get you guys the projected dates of the test here in just a little bit, because that was one of the things that I had written down as a note, but I didn't manage to look at the calendar.
So how are you doing the exams?
Well, for you guys, we're going to do a midterm and a final. I probably, for you guys, when you guys are out at your place, and actually, Morgan, you too, if there's somebody who could proctor it for me, like a boss or something, and that way you can, they could do it from that.
Can we do the preview, the website?
I don't have access to ProctorU.
You don't? Okay.
Yeah. I don't have access to ProctorU. So basically, I just need somebody to give you the test and say you did it in a time period, because it's going to be open book, open notes. I just don't want you connected to the internet. No check, just the open book, open notes is fine. So take good notes, okay? That's the key. And with the recordings, you should be able to take the notes on off the recordings as well. All right.
That's the best way to study.
Well, Chegg's not always right, okay? Chegg's not always right. And if we start with just mechanics, we're concerned with the state of rest or motion of an object or body. Okay? So we're dealing with an object or body. So in this class, we're going to deal with two types of bodies. One is a particle, and the other is a rigid body. So on the particle, you can think of, even if I had a wheel or a hoop, that I'm dealing with the idea that I can track the center of mass, okay? Because we all know, if I was in good old physics class and I had my book, even though it's hanging off the edge, as long as my center of mass is above the edge of the table, the book's not going to fall off the table. It's when that center of mass creeped over the edge that I was going to get the book to fall off the table. So the thing about it is I really want to be following it as a particle. So as a particle, I'm kind of tracking as a center of mass. So you can kind of think of it this way. If I'm looking at the solar system, there's the sun, and here's the Earth. Because of how far away the Earth is from the sun just sees the Earth as a speck. And so that I can look at it as a speck, and I can be dealing with it as a particle. So the first sections of these chapters, we're going to be analyzing motion as if something were a particle, because we're going to do that particle part. The rigid body starts taking into account that I've got an object that is going to have some size and some mass to it, some sort of volume, and the size of the object is going to come into play. We can do a couple of different things, like what we did in statics, where if I have my water tower I have a shell and a vessel and a funnel coming down here, I could do those three pieces. But now if I'm starting to put this into motion, I gotta worry about things a little bit. I gotta worry about other aspects of of what's happening that I didn't have to worry about before. So we're going to be looking at, and the thing about a rigid body is, think the wheel on a railroad train, okay? I don't get a change in shape. It doesn't deform. So if I push on it, I still am going to have a wheel. So if I think of my big rail wheel, it's not changing shape at all. It's not going to deform. I'm not losing anything into that deformation. And so that's one of the things that we're worried about from a rigid body point of view versus the other. What's going to happen to you as you go forward is the next class. It's like fluid dynamics, where I no longer have a rigid body. Things are going to move, things are going to spread out, things are going to have a different aspects. So we're worried about particles and rigid bodies, and we're starting. So in statics, just to remind everybody, because I'm not sure when everybody is where we are. So in statics, our object is usually at rest, but it could also be in constant motion, provided there was no acceleration. So if I looked at it, we had the sum of the forces. Remember, forces are going to be a vector quantity, was equal to the mass times my acceleration, equal to 0, and this was our first condition of equilibrium. Our second part of it than it is in the engineering part, and we used M, right? And we used D, so I'm coming back to the physics part of it where we talk about torque. And remember, in torque, this is my moment of inertia. And this is my angular acceleration. And that had to be 0 as well, whereas this was a vector quantity and that was a vector quantity. So even though we ended up dealing with the moments and we simplified things a lot, it comes back from the fact that if I have torques, I have that angular acceleration, and as long as I'm in statics, as I had no acceleration, I could still be in constant motion. I just can't have an acceleration. And that's where we were, and this was our second condition of equilibrium. So we have that piece. Now, other thing we have to worry about, and this is going to come into play that we didn't play with it quite as much in statics, but we were going to start playing with it. Remember that torque, which gave us the moments, is related to R cross my vector quantity. So we're going to have to recall our vector aspect of various pieces. And so if you haven't reviewed cross products in a while, cross products are going to be in Appendix D or Appendix B. It's in the Hibbler static section 4.2, but it's also in Appendix B. So you've got a place to go back and look at the cross product aspect of things. So that kind of gets us the differences between statics and dynamics. Okay, we're all going to be off of the chat for right now. I was just making sure it worked. Days going forward, but we'll get it going. Typically, we're them in accelerated motion.
Constant acceleration?
Potentially. So, and we're going to do like we started back in engineering physics. Okay, remember in engineering physics, we do it in two parts. We started out with kinematics, but we didn't care what was causing the motion, right? We didn't knew we had motion. And if you guys remember, that gave rise to equations like this: v squared is equal to v in position. We had v is equal to v initial plus at, and we had a change in position which is equal to v naught t plus 1/2 at squared. And we ended up we derived those equations. We also looked at the difference between instantaneous and average. Instantaneous gave us our limit as t was approaching 0. And I will tell you right now, depending on which dynamics book you pick up, Hibbler doesn't go into this as much. I have 3 other dynamics books that really start with the limit for the instantaneous part. They really go back and look at that aspect. They're actually going back and teaching it from a more vector analysis. Our book, he's actually just jumping right into problems, okay? And he's expecting you to remember that, okay, I have an instantaneous and I have an average, and recalling that particular aspect. So we do want to look at that piece. And then we're going to start with the kinematics, and then we're going to go to the Newtonian, where what's causing the motion, what are the forces that are involved, and we're going to make that same progression that we did in engineering physics. So let's kind of go back, and I'll get you a couple of definitions just so that we have the definitions. So by our author standard, a particle has mass, but the size can be neglected. And the geometry of the body is not involved in the analysis. A rigid body is made up of a combination of particles. At a fixed distance from each other, and the shape does not change. So that's our difference between a particle and a rigid body, and we're going to start with particles. We're going to start with particles. And our book gives us a problem-solving strategy. First is read the problem. And in this one, as we start progressing through the book, you're going to want to be making some choices and some analysis. You want to look at it as what's happening. And in this case, it's specifically looking at it as a particle going to work? Is a rigid body going to work? Is my coordinate system going to work? And then, as I always say, draw the picture and label. And include things like the not specified knowns. Specifically gravity, and if we are in meters per second, you want 9.81 meters per second squared. If you're in gravity in the English units, you're going to use 32.2 feet per second squared. So that's one of the things that you got to kind of look at and make sure you've got those pieces. And this was, so as I'm doing this, and finally at 3, after you've drawn and labeled, you've got to commit to your coordinate system. Then you want to look at what principles might, and even though we just started out with those 3 equations that we used all through physics, you're going to find that now we're going to throw a lot more calculus in it. And not only are we going to throw a lot more calculus in it, we're going to manipulate the equations a little bit more. And that's where I said I'm a little rusty, because I haven't had to do it in a while. So you're going to have to, so if you've got your calc book, you may want to have access to it, because you may want to go back and look at a few things. I've actually, in my notes, as I've started pulling my notes together for the class, I've gone back to the mathematical principles to say, all right, let's go back and look at the mathematical principles, because we're going to have to apply them here in the physical problem that you may or may not have had to do before. When you're running the calc problem, you're just running the math. When you're running the physics problem, you've got, well, I've got my equation, I can plug it in. Well, now you're starting to get a little bit more complex, and so we're starting to get into those mathematical methods that you may not have done a little bit more. Then you have to define, now they recommend, and this is one of those strong cases where you're going to have to make a decision when you cut and run, is you want to take it as far algebraically as you can. And you're going to have to decide, because you want to solve to plug in and you want to watch your units. And the unit analysis is going to help you out. It's going to make sure you haven't made a mistake along the way. You want to watch significant figures and kind of how you're going to carry those through. Ultimately, you're going to solve, and then you're going to question, does it make sense? And luckily for us, this is a case where, because we are using mastering, mastering's going to tell you pretty quickly whether or not something makes sense or something doesn't make sense. It's gonna give you a or not, and we're gonna be looking at where things are. And I will tell you already that our book does something that's gonna drive us all nuts. Okay, I don't know why he's done it this way, but he has. So we're diving in. And we're looking at going back and saying position. Remember, position is going to be related to where am I? And displacement is my change in position. So remember the old toss the ball up and having it come back down and catching the ball? The change in position, and he uses S as our position, so he's actually using S. The change in position in this case is going to be 0. Didn't matter that the ball traveled up and it came back down. If I'm looking at my change in position for this situation, I'm at the start and the stop. So, yeah.
But it's possible to change positions horizontally, but not, or change positions horizontally, but not vertically.
It's possible both ways.
Okay.
It's possible, this one is if I toss the ball up and I'm only looking in the Y direction, I've had no change in position. I could look in the X direction and I have had a change in position. You know, it's really hard to draw your picture to show it that way. So I can have a change of position in the X direction. I can have a change of position in the Y direction. I can have a change of position in the Z direction. Okay, or I can have a change of position in the R direction if I'm doing spherical coordinates. So I can have a change of position. So that's why he's using a generic S. Now this is the part that's going to drive us all insane. Because if you look at where he defines it, he starts with this notation. Okay? He starts with that notation, which is going to drive us nuts because he's meaning this to be final. But then he's going to give you a problem later on in the book where he's going to do it this way. The notation that we're normally ready for. Okay? But then he's going to do something a little bit later that's going to tell you that this actually means that. To me, that's sloppy book editing. Okay? Or you're going to also see this. Okay? Just be aware, you're also going to see this. You're going to see this notation as well. So I'm giving you a heads up right now that you're going to have to pay attention to our author because our author has mixed notations. Again, that's to me a sloppy book editing. I will try to be very consistent because I like to do this, okay? And I like to put my final and initial in. I am one, and now I may mix this up just so you guys who haven't had me before. I also will use the I instead of the not. I'll use them both, and I'll use them interchangeably. But I think that's I'm not as picky about that one. Yeah.
Would you use S prime to equal ds over dt?
When we get there, potentially. Okay. I still like writing out especially where we are now. But by the end of the 6 weeks, we may be using this kind of notation. We may be using this kind of notation. So I'm just giving you a heads up because I'm going to try to be consistent with the book, but this part drove me absolutely insane when I started preparing my notes for teaching. Because it's like, okay, and then not 2 sections later, he's changed the notation. So I'm giving you guys a heads up as you guys are reading through, just be very careful as to how he's doing the notation. Okay? The other thing is, this is a vector quantity. And you'll see that we're not putting the vector symbols on, and he is not necessarily bolding it. He's not necessarily putting the vector symbols on top. We are going to have to accommodate and take that into account. So this is strictly a notation issue for the book. Okay? So, just giving you a heads up to start with. So here we go. So we're going to start with our change in position. And that's going to be my final minus my initial, okay? So we've got our final minus my initial, and we know that velocity is equal to a change in position with respect to time. And if I go ahead and use my calculus, I'm going to use my differential. All right? Now, dt is always positive. So ds can be positive or negative, and this is going to tell you direction. So positive can be up, positive depending on how I set my coordinate system up, positive could be up, positive could be down. It's how I set my coordinate system up. Typically, we use positive as up, negative will be left, negative will be down. But again, it's how you're going to set up your coordinate system for your situation. Because remember, we don't necessarily just go up and down. If I'm on an inclined plane, I could be going perpendicular or parallel. Okay? And I can switch my coordinate system to allow for that. I can actually switch it. And remember, magnitude, if I'm looking at velocity, magnitude usually relates to speed. So I can have instantaneous, and I can have instantaneous, or I can have average. So where we are is this right here is our first equation, and this is given as 12-1 in the book. Okay, 12-1. And then we go next. We know acceleration is dv dt, which then becomes which gives us and so far everything's familiar. They haven't really changed anything, just kind of writing some stuff that where we were way back when. Now, if the particle is slowing down, it's decelerating. And just kind of as a reminder, if I do a change in velocity, or v final minus v initial is negative, this is going to end up giving me, it's slowing down. And it'll ultimately give me a deceleration. So if I do dv is equal to ds dt, and I'm going to now change this to dt is equal to ds over v. I can also have acceleration is equal to dv dt, which also means that dt is equal to dv over a. dt is equal to dt. I can get ds over v is equal to dv over a. And now I can have a ds is equal to v dv, and this becomes 12-3.
That's the equation that's given in 12-3 is what we're saying.
Mm-hmm. Mm-hmm. So we actually have something that's a little newer than what we've seen before. Then we can get some of our kinematics equations. So if I have dv dt, and now I'm going to integrate from v initial to v final dv, which is going to give me from 0 to t a dt. And this is if acceleration is a constant. So this gets to when acceleration may or may not be a constant. Now when we go back and we wrote those three equations for kinematics, that's what acceleration was a constant, and we knew what that constant acceleration was. Now, because I have written it this way, I don't have to have acceleration as a constant. Acceleration can be a function of time. Acceleration can have a time curve. Acceleration can have something else. But if acceleration is a constant in this case, we can do the integration and we get v final minus v initial is equal to my acceleration, which is a constant, and that's why we use the little c to show that arrow. And now I get v final is equal to v initial plus acceleration times time, which is the kinematic equation we've known and loved. But here, this general equation right there, acceleration does not have to be a constant. Acceleration does not happen to be a constant at that point. And this happens to be 12-4, if you're keeping track in the book. And now we can do the same thing, okay? We can go in and we can do the same other stuff. So I'll start with v is equal to ds dt. This gives me the integral of v dt is equal to the integral ds. I'm going from 0 to t, from s initial, end up with, but now I can plug in that this is v plus 2 minus s initial. This will end up being vt plus 1/2 a minus s initial, and this gives me 12-5. Now that fun little equation that I used derived just a second ago, I can go from 0 to the final velocity v dv is equal to s to s a c ds, where that's a constant. Okay, it's a constant. This will give me my v squared minus my v initial squared plus, or equals 2a, my change in position. And this is 12-6. Again, the key is this is when it's constant, but I can start playing with these equations and acceleration doesn't have to be a constant. We can now start taking into account other things that are out there. So a couple of reminders at this point, just so that you have it out there. And if you look at another dynamics book, the other dynamics book will start out with this. If I have where m is a scalar to the vector, okay? So m is a scalar to the vector. It is not a vector quantity. I can have this, oops, sorry, that's not a t, and we'll want it du. Okay? This is just generic form from the calculus. So I get this so this is taking into account vector quantities. I can do vector A plus B du is going to give me then if I do the scalar product, and then I can do the dot product. It's a cross product. So just as a reminder, how I deal with vectors, just kind of a refresher as to how to do that, because it's not necessarily summed up in your calc book very well. All right, you guys ready to do a couple problems?
Can you please leave that on the screen at the bottom, wait
Okay.
for just a moment, please? That's times B over there, right?
And that's cross product.
Okay, got it, thank you. All right, I'm good.
All right, so we've got a ball thrown. Upwards with a speed of 15 meters per second. Determine the time of flight when it returns to its original position. So I've got my ball that's going to go up, and it's going up at 15 meters per second. We know it's going to travel, and it's going to come right back down. We have an initial velocity of 15 meters per second. And this becomes one of those things that they haven't mentioned anything at all about gravity. You go in and look in the book, hasn't said anything at all about gravity, hasn't even thrown it in there, hasn't had a discussion, it's not in the example, we haven't seen anything. And so all of a sudden you're expected to remember, wait a second, I do have an acceleration. And its acceleration is 9.81 meters per second squared. This is where we're going to take that step from our entry-level books into our mid-level books, in that there are just certain things they're going to assume you know. And they're expected, you know, they're not going to mention it at all, and you're going to start trotting down, and you're going to say, okay, those things that may or may not necessarily be there that is specified. This is a constant accelerant. I can use one of the equations that I've derived, right? I can constant. We know our initial position minus our final position is going to equal 0 because that's stated in the problem. I've got an initial velocity and t, and now I have my 1/2 my constant acceleration t squared. So odds are I'm solving for t, so I'm going to go ahead and use my quadratic formula. And I'm just going to write it out in its general form because it'll be helpful later on. Just a sec. Yep.
On that middle equation where it says 1/2 AS.
That's AC. It's a constant acceleration.
Acceleration constant. Okay.
Yeah.
Thank you. Did not know what that C meant. Thank you.
Yeah, it's a constant acceleration.
Okay. So it does not, in this case, it doesn't change, but in dynamics, the acceleration can change.
The dynamics acceleration can change. We may or may not have a constant acceleration.
Yeah, that's a quadratic formula.
Huh?
I said that's a quadratic formula.
Yeah, that's quadratic formula right there. So that's 0. So now we can plug in our numbers, right? So I'm going to end up with t is going to equal minus my initial velocity plus or minus the square root of the initial velocity squared plus or minus 4 my acceleration divided by 2 times 0 because my c is 0 divided by 2 times my acceleration divided by times 2. So now I can get that. I get minus v plus or minus v divided by a, which is going to give me my two solutions of 0 minus v over 2a. This is when we start. This is the one we're really after, so we have to make that assessment. So now I end up with a minus 2, 15 meters per second divided by minus 9, that being 3.06. So, yeah,
Quadratic is -4 times a over what?
2. It's the 1/2.
So that was just kinematics.
That was just straight kinematics.
It's like chapter 4 back in physics.
You got it. We haven't done anything complicated yet. Yet. Have to dust off stuff, It's been a whole 3 days since we did anything, right?
Seems like
No, it doesn't.
It's been a whole 3 days. Okay. All right, so now we're going to do a rocket problem. This happens to be problem 12-18. So if you actually want to go in and read the problem, it happens to be 12-18.
what was the other problem?
I don't remember. I've been pretty good in my notes actually writing the problem numbers down, but not that one.
It's okay.
All right, so we're given a rocket. And so our rocket is actually, in this case, the acceleration is given by 6.02 s. No longer have constant acceleration. Okay, no longer have constant acceleration. So you're going to have to go through and figure out which way you're wanting to get there. And the way this problem is working towards is we want to know the time that it takes, time to reach 100 meters. You want to know the time that it's going to take to reach 100 meters. So I'm going to end up doing two different equations, okay? I'm going to end up doing two different equations. One, I'm going to look at ds is equal to the velocity times time. Because ultimately I'm going to know ds, and time is what I want to know, but the problem is this is my straightforward part, but I don't know velocity. So I'm going to have to go back and figure out velocity, and I can go back and figure out velocity by doing this one. dv is equal to my acceleration ds. I'm given my acceleration, so this is going to be 6 plus 0.02 s ds. This is going from 0 to some velocity. And this is going to go from 0 to s. So we know that this is going to end up being v squared over 2, evaluated from 0 to v, which is going to just give me v squared over 2. When I do this integration, I'm going to get my 6s and keep it as 0.02 over 2 s squared. And I'm going to evaluate it from 0 to s. Now I've left it this way for a reason, because I want to simplify this into something more manageable. So I get v squared is equal to 12s plus 0.0.
Thank you.
Now things are going to get funky. So v is going to equal 12s plus 0.02 s squared to the 1/2. But I'm going to plug that back into here. So I'm going to end up with the integral of ds is equal to the integral of 12s plus 0.02s squared 1/2 dt. First thing we want to see and notice is that this is a function of s, and I'm in the dt integral. This is a function of ds, so I've got to get this over here. So now I'm going to get that. So I'm going to get my ds 12s plus 0.02s squared to the 1/2 is equal integral dt, which is going to give me t. Okay, in the back of your book, in the appendix, there are some integral tables. In your FE manual, there are integral tables. In your calc book, there are integral tables. They are going to become your friend. Because this isn't pretty to integrate. Okay, this is not pretty to integrate. So if I go to Appendix A, I'm going to find this. I'm going to get dx, the square root of a plus bx plus cx squared is equal to 1 over the square root of c, the natural log of the square root of x plus cx squared plus x square root of c plus b 2 square root of c
Would there be a plus constant of integration along with that, or is that just it?
That's what the integral table gives me. And we're going to evaluate this from 0 to, we're going to evaluate this because we want to know where we are at 100. So those are going to be our integral limits that we're going to play with. So we're not going to have to worry about that constant of integration because we do have those limits.
Yeah, I got you.
So that you guys, or Appendix A, it's actually Appendix A in your book. Okay, so keeping that in mind, this is what we get. I get 1 over the square root of 0.02, natural log, oops, I did this wrong. That bracket's not there, that bracket's here, sorry. Natural log of the bracket, the square root of 12s plus 0.02s squared plus s square root 0.02 plus 12 2 square root of 0.02. So the way I did it is I evaluated at 100 meters. And this becomes 7.07 natural log the square root of 1200 plus 200 plus 14.155, which ends up, when you plug all the numbers in, you end up with 32.28. At 0, you still get the 707, except now you get the natural log 0 plus 42.55. And this gives me 26.52. So t is going to equal 32.28 minus 26.52 is going to give me 5.76 seconds.
That's the answer, how long the flight time was.
To get to 100 meters, yep.
Oh, or how much it takes on to
We'll do one more and we'll call it good. All right, this is problem 1231. We're going to be given the velocity is going to equal, let me write it out again. V is equal to V naught minus Ks. S is equal to 0 at t is equal to 0. We want to find the acceleration, the position as a function of time. So I'm going to start with ds is equal to my velocity times my change in time. Yep,
on that equation, is that V, what is that, minus KS?
k, it's a
What is-
constant.
Oh,
It's just a constant.
It's just a constant.
It's just a constant. So I'm going to end up with ds is equal to v minus ks dt. I'm going to have to put this on that side, so I get ds v naught minus ks. And that's ultimately going to give me my time variable. Okay, so I go to appendix B. And I find that dx is a plus bx is going to give me 1 over b natural log a plus bx. So that makes that integral easy to do. So now I get minus 1 over k, because b is k. There's the negative, gives me that. I get the natural log v minus ks evaluated from 0 to s. So now I get minus 1 over k natural log v minus ks minus 1 over k natural log, because if I put a 0 in there, I'm only left with that. So now I have minus 1 over k natural log v minus ks plus 1 over k natural log v. So some reminders, I'm not done. Even though I have a function, I'm not done. I have to clean it up. So recall the rules of natural logs. Natural log of x over y is equal to natural log of x minus the natural log of y. Natural log of x times y is going to equal the natural log of x plus the natural log of y. Natural log of x to the y is going to equal y natural log x. Natural log of e is equal to 1. Natural log of 1 is equal to 0. Because the first thing I'm going to do back up here is I'm going to factor out the 1 over k. I'm going to put the positive in front. I'm going to put the negative in back. And now I'm going to end up with 1 over k k natural log of v naught minus ks. But still not necessarily clean. And if I go look in the back of my book, that's probably not the answer I'm going to see. So now I'm going to clean this up here. I've got t is equal to 1 over k natural log v naught minus ks. I'm going to multiply k over here, so I get kt is equal to the natural log v naught minus ks. I'm going to do the e on both sides, so I'm going to get ekt is equal to v minus ks. I want to solve for s because I want s as a function of t. So I'm going to end up with v naught minus ks is equal to v divided by e to the kt, which is going to be v naught e to the minus kt. And now I can just solve for s, and I'm going to ultimately get s is equal to v naught over k 1 minus e to the minus kt. Now things become a little easier. Because to get v is just ds dt. And when I do that, I'm going to get v naught e to the minus kt. And then a is just dv dt, which is going to give me a minus v k e to the minus kt. And I'm going to stop there because the next one's hairy.